Hello, and welcome to Lab 5, The Falling Slinky. Introduction. So the purpose of this lab is to analyze the motion of a stretched slinky dropped from static equilibrium, and the video is a video of a slinky falling. As a slinky falls, the goal is to determine the effects of gravity and drag to predict the motion, using fundamental principles. These fundamental principles are the velocity update formula, V final equals V initial plus the net force over mass times the change in time. The position update formula is the final position equals the initial position plus the average velocity times the change in time. Drag force is the force of drag equals the negative drag coefficient times velocity. And the force of gravity is, in vector form, 0, negative mg, 0. So on the right, you can see a video analysis of the tracker. So the initial conditions for the tracker are the calibration length is 1.75 meters, the mass of the slinky is 0.204 kilograms, the initial position is 0, in component form 0, negative 0.003, 1.223 meters, the initial velocity is 0 because it starts at rest. Now for the computational model, here are the initial conditions. So I inputted in the spring mass in kilograms, the initial position, and the initial velocity, which is all 0 because it starts at rest, and then the drag proportional constant, and this was calculated through trial and error which one gave the best fit. Next is the code for the simulation. So for this time, this is the time until the top reaches the bottom, and the next would be the net force, which is the force of tension, and that is opposite to gravity, and then the weight force, which is weight equals negative mg in the j-hat direction. Then for the momentum principle, we use the velocity update formula from the fundamental principles and the position update formula. Now, this is the next time jump, which is the time of lapse observation of the tracker, and the drag force is included in this computation, and the weight force stays the same. The velocity update and position update stay the same with the new position. Here's the observational model and the model predictions. As you can see, the model matched fairly well with the predicted motion, except for the parts in the middle. The first part was exactly perfect and spot on because the slinky is at rest and therefore not changing position, so there should not be any error there. But the error in the middle could be attributed to a number of things, but it could be attributed to errors with the tracker or with the calibration. And in the model, the orange line is the observed line and the blue line is the predicted line. So, what does it mean? So the question posed is, why does the bottom of the slinky stay stationary? The bottom of the slinky stays in position when released because the tension force of the slinky is actually equal to the force of gravity during that part. The slinky's bottom is in static equilibrium, meaning the two forces are equal and opposite to each other. There's also a 0 net force, so the bottom stays motionless until the entire slinky reaches the bottom. And in that picture on the right, you can see sort of a diagram of what's happening. The bottom is staying at the exact same position while the top is moving down to reach it. Another question posed is, does the predicted model satisfy the energy principle? The energy principle being delta E, the change in energy, is equal to the work done. And the answer to this is no, because of the fact that there is a non-zero change in energy. The increase in kinetic energy after the slinky is let go creates unbalanced forces due to its motion, because when the top meets the bottom, it starts to move down. Thank you.